Thank you very much, everyone, for coming out. I'm going to talk for about 20 minutes, and I'm going to talk to you about energy and energy transition, and I know you're all going to be absolutely riveted by that, so the fact that you're standing up and drink in hand, if I see you sneaking out for another drink, I will not be offended by that at all. But the reality is energy transition is something that people talk about a lot, and you'll hear about a lot of stuff, and it's written in the newspaper, and you'll see different opinions about whether renewables are good or bad. And the reality is it's actually a lot more complicated than just, is it good or not, or should we do it or not? And what I want to talk to you about tonight is give you a little bit of background, what's actually happening in the context of energy transition, what it actually means for Alice Springs, and then how does the Alice Springs Future Grid project fit into that, and give you an insight as to where that takes us and why we think this is a great opportunity. I'm going to spend a little bit less time talking about what we do in the project because, frankly, it's pretty geeky, and unless most of you are power system engineers, you're not going to get that excited about it. But I will try and give you a high-level sort of insight into some of the things we do. First of all, I need to note that this is a consortium project. It's a project that has come together. It is funded with about $5.5 million of funding from the Commonwealth through ARENA and the Department of Industry, Science, Energy and Resources, funding directly from the Northern Territory Government, and then about $4 million of in-kind contribution from our project partners and consortium members, including Ekistica, DKA, CSIRO, Power and Water Corporation, TGen and Jacana. We've also got involvement from ALEC and CSIRO, who are putting in significant contributions into the project. On top of that, we then have a whole bunch of interactions with different members, the different industry sectors as well, who are bringing in knowledge and capability. So it is quite a broad project. That includes groups such as Horizon Power, University of Technology, Sydney, RMIT, and different industry bodies that are supporting it. So it's a lot that we're bringing together. And really what I want to be able to outline to you is why do so many people want to get into a room and talk about energy as we have been doing on this project. So one of the things you have to understand is that we are operating in a very rapidly changing environment. We use the word transition, and I used it very deliberately in the title to this presentation, but I use it tongue-in-cheek because we keep talking about transition as though it is something that is smooth and linear, and each year it just gets a little bit different, and we just slowly move through it. The reality is we are in an energy transformation environment. That's what's going on. The changes industrially that we are experiencing in the context of energy are as significant as the original industrial revolution. So the evolution of steam trains through the 18th century, 19th century, it's that level of change that is going on. One of the favourite quotes that I like to use around my civil engineering colleagues is this one from the London City Press in 1864. The engineering world is literally frenzied with excitement about railway development. We'd no sooner enter a lunatic asylum than attend a meeting of the Institute of Civil Engineers. If you read back in the day, in the 19th century, the way people talked about trains and the civil engineers and all the rest, it was a lot of the same language that we see being talked about in the context of the new energy transition. And so I use this frequently with we're talking about with electrical engineers, go, look, we sound like a bunch of lunatics when we talk about this, and people don't want to listen to us. So it's actually really important that we're able to communicate what's actually going on. Now, the challenge is that we are working in an innovation space, and innovation is a word that is used by a lot of different people, and it's often used to mean a lot of different things. But the context of what I'm going to use it for is about understanding change. And the reality is in a changing environment, some of the innovations that people come up with look decidedly weird. So this is a tractor that was patented in about 1892. So if someone wants to fact check me, you can. It was before 1900, I know that much. But they patented this, and it's pretty bizarre looking. The engine and the drivetrain actually sit inside the main wheel. Now, this is bizarre, and the company ultimately went out of business. They clearly couldn't sell a tractor out of that. But the reality is some innovations, however crazy they look like, actually drive innovation elsewhere. And so this is a facility in Idaho that is actually sponsored by Caterpillar, and it is the US National Laboratory for Tractor Development. And this national laboratory. It's actually funded by the US government with support from industry. The sole reason it exists is because of that tractor, and everyone realised how bad it was and how bad it was for consumers. So sometimes bad ideas actually lead to good outcomes. And it's an important thing to realise that as we're operating through that transition, sometimes failure is an okay thing. What matters is what comes out of it. Sometimes it's a good idea, but at not the right time. Now, this here is a vacuum tube. It's a vacuum tube that is made out of leather. A guy called Isambard Kingdom Brunel, who was arguably one of the greatest engineers of the 19th century, came up with this idea that said, we spend a lot of energy with trains, and I'm sorry, you're probably getting a bit of a sense about old, like 19th century trains and tractors out of me, so yes, I'm a geek, I'll admit it. But he had this idea that so on a train we spend a lot of energy moving the actual locomotive and then all the coal that goes along behind it. So what if we have the engine at one end of the line and we suck the carriages all the way along? And so the idea was that you'd have a carriage that sat on top of that with a little buckle that sat inside there, and you'd create a vacuum and it'd suck the carriage from one end of the line to the other. It didn't work, not very well. But sometimes good ideas come out, but it's just not the right time. This is Elon Musk's Hyperloop. It has now got a market capitalisation of some numbers of tens of billions of dollars, and they have actually deployed these vacuum transportation systems under Las Vegas at the moment. You can go in and drive in them. So sometimes you'll hear about ideas, you go, that is bizarre, but it's not that it's bizarre in and of itself, it's just other things need to catch up with it. Thirdly, when we're talking about change, we want to see a perfect transition. We want to see everything very elegant, very neat, very ordered. And sometimes we don't understand the challenge between elegance and utility. Now, who here is older than 40? And I can put my hand up. Yes, there's a couple of you who I know are older than 40 and you're not putting your hand up. I'm not going to look in your direction, Jody. But some of you may know what that is, Betamax. And the reality is for those of you who are younger than 40, there was a day when before Netflix, you actually had to hire stuff. But the reality was that Betamax as a technology, as a platform, was a far superior platform to this one that we all got to know and love, the old VHS. And so sometimes because there'll be a bunch of different companies who are saying my product is best. But elegance in a changing environment doesn't matter unless you understand utility. And in the end, the VHS tapes destroyed Betamax because it was so much easier to use. Customers liked it. It was easier for them to engage with, and the products were cheaper. So we have to understand that in changing environment, elegance and the perfection of an idea isn't necessarily the ideal end outcome. Now, the context then of how we respond to technology change is that we actually have three main responses to technology change. Denial. It won't work, won't happen. What about the cost? In the 19th century, there was something called the Red Flag Act. It was actually one of the few acts that was launched concurrently both in UK and the US, and they copied each other's language. The Red Flag Act mandated that, yes, once again, it's going to be about tractors, that if you drove a tractor or a locomotive, that you had to have someone walking in front of it at all times waving a red flag, just in case anyone would get run over. Now, we think that is absolutely an absurd with the context of cars and all the rest of it. But the reality was that that was written into legislation by people who said very passionate things about very passionate ideas and worrying about people dying because of change. Denial's easy to laugh at, but it is something that you actually have to be aware of. What happens though is that when you argue against denial, what you often end up with is substitution. And in a substitutional environment, it's an environment where you say, well, we'll accommodate that change. We see that change solely through the lens of efficiency. And we understand that it's all about the technology. It's all supply side driven. It's assumed to be linear in its transition. And it assumes that everyone who is in the room, their roles and their positions of influence within whatever that industry sector is, they all stay the same. And in many respects, what we've seen over the last 10 years within energy is people arguing about denial, but actually settling on substitution. because most of the main power companies in the country are the same power companies that we had 10 years ago. AGL, Origin, Energy Australia, Pac Hydro, Redflow, not Redflow, anyway, another one. They're many of the same companies that were there previously, and they're just doing what they did before, but now they do it with a bit of renewables, and it's a bit more efficient, and it's a bit cleaner. And fundamentally, their position, their voice in the room hasn't changed. So as much as you can fight denial, sometimes you end up just in a substitutional environment. So the third wave, though, the third response is transformation, and this is actually what we're starting to see emerge more substantively. Transformation asks the question is, what are the things that we can do now that we couldn't do before? What is it that is necessarily that it's adaptive and non-linear? It doesn't move just in steady orders. It actually changes rapidly and it'll stop and it'll consolidate. It's demand driven. It's all about consumers saying, I want this, rather than suppliers saying, you must have that. It challenges how value is defined, and value as far as consumers, what do they want? How do we understand it? When you think about the power system, for 100 odd years, you got a power bill, and that was just what happened. You used energy when you wanted to use it, and you got a power bill, and it told you this is how much you used for the last quarter. We now live in an environment where you can say, well, I care about how much it costs, but I also care about where it comes from. I also care about when I use it. And actually, the value, it changes the utility that we have with it. But most importantly is influence within the market sector becomes asymmetric. That means that the people who necessarily have the most money invested don't necessarily have the biggest voice, but equally some of the people who have the most influence don't have as much at stake. And that asymmetry is what changes the entirety of an industry. It's what changed the railways, it changed agriculture as people started to understand what was going on. And agriculture is a really good example. We saw it happen here in Australia, that when first we had mechanised agriculture, you had a whole bunch of people say the old way of doing things are better, and they were very firmly in the denial camp. Then there was a bunch of people who ran the same size property they'd always run, but instead of having 10 labourers and a handful of horses, they had one labourer and a tractor, and they were like, well, I now run exactly the same property I always did, but just more efficiently. And then what you get is the group of people going, hey, I can now run, instead of doing 10 acres, I can run 100 acres. Instead of running 100 acres, I can run 10,000 acres. And that was when people started to go, how do I use technology to change what it is that I could do? So this is not energy related, but it's common to every industrial transformation we've had. But it is really, really important to understand that this is what we're dealing with right now. So how is generation changing? First of all, traditional generation was built largely on 5 axioms, 5 core ideas. If you're going to build a power station or a transmission line, it's better to build bigger than it is smaller, because it's really hard to augment these things. So if you're going to build it, just build it really big. If you're going to build it, always build it today, not tomorrow, because concrete, steel, labour, copper, it's always going up in price. So just build it big, build it today. And when you build it, your operating cost will be more than 50% of the life cycle cost. In fact, most of the large power stations and transmission lines, your operating cost is probably closer to 60% of the life cycle cost. So once you've built it, you've got a fair amount of variable cost that you can deal with. You've got a high certainty over a very small number of generators, and it is fundamentally defined by the electromechanical physics. So we're going to get a little bit techie here, but it's defined by how big, heavy things spin. That's the entire power system. What you consume at home is defined by how really, really big, heavy things turn around and what happens when you try and stop them from turning around. So what's actually happening though? What does renewables actually look like? Renewables are modular and scalable. The reality is that a power station, if you build a power station 10 times bigger than the one you're planning on building, you'll probably assume that it might cost half as much again to go with that order of magnitude of scale. But you can put 10 kilowatts of PV on your roof or your business, and it'll cost you about $1.20 a watt. I could do a 10 megawatt solar farm, so 1,000 times bigger, and it will probably cost you about $1.15 a watt. I could do a gigawatt solar farm 100 times bigger, and it would probably cost you about $1.05 a watt. So you're having these massive orders of magnitude of scale, but the price isn't coming down. So it's actually means that you can put the technology in places that you wouldn't normally put it. The prices continue to decline. I work on projects now where we are building financial models and writing contracts for hundreds of millions of dollars, where the assumption is that by the time we ink the contract And in fact, by the time we ink the contract with the supplier and they then ink the contract with their suppliers, that the prices will have dropped. And everyone's betting on that price. And there is not a precedent in history for that level of sustained price drop, because it's been happening every year over and over and over, COVID notwithstanding, which did screw global supply chains. But generally the price is going down. CapEx is greater than 90% of the life cycle cost. So once you've built it, there's 2/10 of not much to spend to maintain it, but all of your decisions have been made on day one when you built the thing. So once it's there, it's really hard to change what's actually going on with it. You have a very low level of certainty about what any of the houses are doing. The largest single power station in Australia right now is it's about 3.2 gigawatts. So that's 1.5 times the size of what the Snowy 2 program is going to be. It's roughly equivalent to half of the entire New South Wales load. So the biggest power station, 3.5 gigawatts, is actually 2 million households. 2 million households have got PV on their roofs. That's the biggest single power station that exists in Australia right at the moment. But we don't know what all those households are doing. So we've got 2 million power stations that we have no idea what they're doing on any given point in time. And so it's a really quite different structure to operating wind, and fundamentally defined by electronics. This is all about what's happening in ones and zeros, bits of electronics inside inverters and inside different bits of power station equipment, rather than big spinning things. So different skill sets are actually involved in this. And what you see when you look at that is you realise that the argument about whether renewables can just replace traditional generation is fundamentally wrong, because it presupposes that they're identical. It presupposes that they're just substitutional. In fact, what you see when you start to look at this is, no, it's transformational. There's a whole bunch of things that renewables can do that traditional generation can't do. And that means there's a whole lot of opportunity with it. But there's a whole bunch of things that renewables can't do that we used to be able to do, and we then need to work out how to respond to that. So it's in that context that we start to understand how change is going on. Now, the other part about this is forecasting change is really difficult. This blue line, the centre blue line that is here, right there, has been the actual capacity in household or residential PV since 2009, when the Clean Energy Regulator came into being. All of these little lines here has been the Clean Energy Regulator's forecast each year all the way along. And you can see that there's a bunch of people who've been paid a lot of money to completely screw up forecasts about change. Because every time they thought, oh, consumers have had enough, they won't want to buy anymore, the numbers go straight back up. And you can see here in 2018, the assumption was, no, it's going to taper off, that'll drop off, it'll pull back. Even during COVID, the assumption was that it'll pull back, and numbers still continue to rise. Forecasting change is really, really, really hard. And I tell people all the time, anyone who tells you with certainty what's going on, you should turn around 180 degrees and walk away from them. The only thing I know for certain is that whatever numbers we put up on the page will be wrong. So you have to be recognising that forecasting is a really difficult element in what we're doing. So how does this impact how we think about power systems in the context of what we're doing here? We can't assume that energy will be valued the same way as it used to be, and it can't be assumed that it'll be valued the same way all the time. It is moving around, and not all the solutions we put in place will work 100% of the time. So there'll be great solutions that are viable and available, but will only operate for certain numbers of hours of the day. And that may well be worthwhile if the price is right. Modality of energy use will be as important as the utility of use. Now, that's a great engineering sentence. Most people probably don't know what it means, but it means how you use it will be just as important as when you use it and what it cost you and all the rest of it. The way it's delivered to you as a consumer will be influenced by what you actually want in a lot more than it has previously. Consumers will change this, and consumers both residentially, but also businesses and large industrial consumers. And we're seeing that in large industrial consumers saying, we will run a processing plant for 8 hours a day, and for that 8 hours a day, we're going to absolutely flog it. But we're going to run it on really, 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 really cheap electricity for that 8 hours a day. And so the assumption around things like baseload as a concept, people talk about it, but baseload only existed because that's what the suppliers needed. And now the demand side is going, actually, we can really optimise our business around that. We can do maintenance for 16 hours. We can drive the business this way. The reality is forecasting resource, forecasting solar, wind, forecasting what consumers are doing is going to be as important as trying to forecast load. and it will be probabilistic rather than deterministic. So we're actually not going to know at any one point in time what one person's doing, but we'll have a high degree of certainty about what's happening in the aggregate. Alice Springs Future Grid, as a project, is trying to operate in that space. So all of that is just an introduction to what Alice Springs Future Grid is, the space we're operating in. Alice Springs Future Grid is not, as a project, here to see where the solar modules work. We did that 15 years ago, proved it worked. Solar cities, as in Alice Springs, we had some of the fastest growth in household PV in the country. We really set the standard nationally for a whole range of things. We know it works. What we're trying to work out now is, well, how do you actually make the rest of the system work around it? So, what does it look like over time? When I talked before about the fact that change is not linear, and in fact it has asymmetry to it, this is what we actually mean. We spent sort of the early part of the 2010s down here where we were just putting in variable renewable energy and distributed PV, and it was going on people's roofs, and it was all relatively straightforward. We could just go on this nice little ramp, and for this bit here, we actually convinced ourselves that it was linear. But then what happened is it came up and up and up and up, and what you tend to find is you get to this threshold point. And once you get to that threshold point, that substitutional arrangement no longer works. You physically can't put more PV on people's roofs because the system will collapse. What that does, though, is then create a new transition where you then start again and you have to start coming in with this step change. And so this is what's happening in our power system. It's happening nationally, it's happening internationally, and it's happening here in the Territory and explicitly in Alice Springs. This step change is a trend that's been observed all around the world. It just happens that in Alice Springs, the limit of substitution has already been found as we are moving into that transformation. So Alice Springs right now is actually pretty much in this position here. Why do I say that? Because we have tested the ideas of Alice Springs Future Grid nationally. Where, as I said, we've got funding, $5.5 million of funding from the Commonwealth. A chunk of that came through, or primarily facilitated through the Australian Renewable Energy Agency, and they looked at our project and recognised that there was a whole bunch of things that are unique to Alice Springs that make it a really interesting test bed to explore a range of transitions. We recognise that the power system of 2030 will require a fundamental set of different relationships between the energy utilities, the JCANA, the PWC, Territory Generation, consumers, different businesses, other players that will come in there. That's not a critique of the way they are now. We're just saying, look, notwithstanding how they are now, it is going to change. And it will require a different way of people working together than what we currently have. And in fact, we recognise that Alice Springs, oddly enough, and it's just a bit of a quirk of history, but we've ended up with the perfect lab bench for the national energy market. We have the same national energy rules that national energy market has. We are governed by the Australian Energy Regulator in partnership with the Utilities Commission. We have retailers, multiple generators, transmission and distribution lines. We have all these things that look like the massive national energy market. The national energy market is the largest single piece of grid infrastructure in the world as far as linear length, and we just happen to have a small microcosm of that here in our backyard. And that means that what we learn here is both valuable for our future, but it's valuable for a whole bunch of other people who want to try things, but you don't just want to go and flick big things on in the NEM because either bad things can happen or the amount of stuff you have to do to actually get a change becomes very, very expensive. And so the Future Grid program is looking at it's a collaborative project, looks at how do we get Alice Springs specifically, but the NT more generally, and with lessons learned beyond that around how do you get to 50% renewables by 2030. Critically, many of the rules and the regulations we have in place at the moment, we know are not tailored for where we need to be. They actually prevent people from talking to each other. So we have used this project as a mechanism to bring a whole bunch of people who in other contexts are not actually allowed to sit in the same room and talk about commercial things because of all the protections that exist around competition. So we've actually had to, in this project, create a space which is overseen by the AER and Utilities Commission to say, yes, you can use this as a sandbox to test things out. So where are we now? I talked before about the fact that we've hit that transition point, we've hit that step change point already. So this was Saturday the 15th of October. Saturday the 15th of October is critical because it was the 4th day last year that we had a record low demand. This is what the yellow demand looks like. So it started at just above 15 MVA, got up to nearly 25 MVA in the middle of the day, and then tapered back off once everyone came home from work, got home from whatever they were doing, air conditioners turned off. It wasn't particularly hot that day, and you can see what that load looked like. This is what solar was doing during the day. So this is actually generated demand from solar PV systems across Alice Springs. As part of the project, we have a whole bunch of modelling and forecasting that allows us to document that. So that was behind the meter solar on that particular day. That blue line is what our generators saw. That's the 4th time last year that that blue line was as low as it had ever been. And that was the lowest it had ever been on history in Alice Springs. So as far as the design of the power system we've got. I'm sure 100 years ago it was lower than that, but for the purpose of the argument, it's its lowest on history. So we had, on that particular day, 6.7 megawatts of load on our generators, 16 megawatts of behind the meter solar, 70% renewable energy being delivered into our grid at that point of time, and 25% of our energy over the course of the entire day was actually provided by renewables. And that's 25% in the context of all of that bit there being provided by gas and all this bit over here being provided by gas. So you can see that's significant. Now 6.7 megawatts, that's just a number. But the reality is we try and run 3 generators at a time because it's always important to be able to have capacity if one generator trips off. That means you've got sort of 2.2 megawatts on 10 megawatt gen sets. If any of you have had an engine and you're trying to, it idles smoothly around 1,000 RPM and you sit there and try and idle it at 500 and it's coughing and spluttering, it just can't get enough fuel in and oxygen and all the rest of it. That's where you start to occur if these dips get too low. And that's what we're actually dealing with. And we don't have, on the NEM, they haven't dealt with this yet. So on the national energy market, they know that this is coming, but it's not there yet because they're so big. And even though you might read articles that says South Australia's gone 100% renewables, it's 100% renewables with 2 really big cables that connect them to the rest of the market that make sure everything else is stable. And we don't have that. So this here is actually pretty scary. But it's actually where the opportunity lies because we knew that it was coming. There was a whole bunch of risk management done around it. There was a whole lot of work preparing for it. But it highlights exactly what Alice Springs Future Grid is all about. We're doing something here that isn't getting done elsewhere. We know Horizon Power, for example, is having some similar experiences in WA, but is in a context where Horizon Power owns, they're the retailer, the network owner, they're the generator, so they can do a whole bunch of things that we can't do here. This is why it's a whole lot harder to try and solve this problem. D uptake is forcing us to move that transition. As I said to you before, the clean energy regulators undercooked that forecast every year for the last number of years. This is where we are right now. This green line is what AEMO is forecasting as a high CER scenario. This is the low scenario, and this is the grey one. And now remember that chart that I just showed you before is based on where we are now. And then suddenly, if everyone just keeps doing what we're doing, we're going to double the size of that problem. That's what we want. Now, as consumers, we all want to be able to put solar on our roof, and we want to be able to have batteries, and we want to do all those things. So we keep saying we want this, but that means we have to solve a problem. We have to solve that problem of minimum demand. So what does Future Grid do? We've got this really beautiful graphic. I'm not going to bore you with all of it, but there's a whole bunch of really geeky modelling stuff that I get very excited about. But doesn't mean much to anyone else. But it's really about understanding the physics of how the power system operates in these modes and how do you describe that so you can start to test it in a digital environment where you can actually go, hey, we've built a model of this. What happens if we just flick that switch and we can see the result without actually causing all of you to lose your power on that particular day? So the modelling part's really exciting for me. Anyway, you can all just yawn through that. We're doing grid-forming batteries out here on the Desert Knowledge Precinct, so we're actually integrating a grid-forming battery here that will allow the entire precinct to go offline at certain times of day. It'll also allow the precinct to provide frequency control and ancillary services into the network. That hasn't been done before in the territory. And we actually don't have a regulatory framework to know how to do that, so we've got a special approval to do it, and then we have to work backwards and go, okay, now that we've done it, how then do you design the rules to structure around this so that other people can do this, whether it's universities or airports or shopping centres who may want to do the same sort of thing. Some of you will have been involved in the VPP trial, which has been around how we understand utilising household PV and batteries as a power station. Can we turn it up and down in response to demand? On that really low day, if we had a whole bunch of batteries that were not charged, we could have said, hey, we want you to all turn on and start charging at that point and pick the demand up. And so the VPP is trying to use that and look at different tariffs that are alongside it. And then future grid deployment is just a generic name for a whole bunch of other things that we're doing around, again, that aren't very particularly exciting, but integrating how systems work. Power and Water has to think about operating effectively a far more open IT platform that allows different systems to interface with it, to pull data out and to send information back, working out how you send signals and do forecasting around that. So that's what we're actually doing around it. What that leads to is that we have to develop a roadmap towards 2030 around getting to 50% renewables. To do that, we need to understand our objectives, and some people will feel very passionate about what the objective should be. Some people will just say, well, it has to be just about 50% renewables. Or other people say, well, it can't be about 50% renewables, it's got to be 100% about reliability. The reality is there's a whole set of objectives that we need to work around, and the project itself is trying to determine the boundaries of what's possible while then working out what the structures are for the plausible. We're not considering every possible scenario. I get asked every time I've done this presentation, are you thinking about small modular reactors? No, we're not thinking about small modular reactors. I'm not discounting the possibility they may work at some point in the future, but it's not a plausible scenario between here and 2030 for Alice Springs. It also establishes the decision gateways for implementing change, and I wrote that sentence, create a platform for multi-objective optimisation in an uncertain environment. Yeah, that's an engineer who wrote it. I'm not going to lie to you. But the idea is recognising that we're operating in an uncertain environment, and we're going to have to deal with a whole bunch of different things that we've got to solve for at any given point in time. As consumers, as members of the public, we have 8 key expectations. We want it to be dependable, affordable, sustainable, equitable, empowering, expandable, adaptable and beneficial. We want all of those things. We also want to pay less. So it's got to be all of those things. And as we map out a plan, we have to have an eye to all of those things. And if we don't, then we'll get lost, because we'll get lost just in this is the best carbon solution, but it's not the best customer solution, or it's the best system security solution, but it's not the best environmental solution. So we have to solve for all of those expectations. We've mapped out 4 key scenarios that we are thinking about. Now, some of you will say, well, what's your assumption around how you're forecasting EV growth? We're not sitting here telling you that we'll forecast EV growth, because just like behind the meter PV, we'll get it wrong. The point is that we've identified 4 key scenarios that are likely to occur. The first one of which is scenario 1, which has high levels of renewable energy on houses and businesses with batteries, and it has very low levels of mechanical inertia, probably moving to a world where we turn the engines off at Owen Springs and Ron Gooden for periods of time. Now, just to be clear, we're not planning on doing that next week, not even next year, but we have to actually go through the thought experiment. It goes, what would it take in that environment? And that means you have to plan for a world where you have engines off, and then you have to be able to start them again. And then once you've started them, you've got to be turning them off, and that creates a whole bunch of challenges. Scenario 2 is still a very high level of renewable energy, but it's still assuming that it's renewables off, but it's assuming that it's all centralised. So large solar farms like your Turn A, all controlled by a TGen or other parties. So it's a very centralised solution. Scenario 3 is assuming that we still focus largely on residential and small business PV, but it's assuming that we keep the engines on. So we're just saying we're going to have that as a baseline assumption. And so scenario 4 is assuming that we have centralised renewables, but keeping engines on. Within those 4 scenarios, we see every possible, plausible future of what might occur. And so we're actually in saying, well, given those 4 scenarios, what does it actually take to get there? And how will you know at different points along the journey that you've gone too far and you now have excluded the possibility of pursuing one of those scenarios? The basic idea is there's only 2 things that we can really vary, is the level of inertia, that's the level of big spinning things that keep everything stable, and whether or not it's more or less centralised. How much control do we have over it, and where is it actually located? They're the only 2 variables we've actually really got to play with in these scenarios. So Future Grid is trying to think about, well, what does that take? What are the electricity rules we'll need to have? What are the training capabilities we'll need to have? What is the technical capabilities we'll need to have? All the stuff that goes in to try and work out what would it take for those things to be achieved. The roadmap ultimately delivers these key things, key drivers, enablers, and splits them out into short-term, medium-term, and long-term. The idea being that we're not telling anyone that you have to choose, this is the only path. We're not going to be Yoda saying this is the path that I have for you I've chosen. It's going to be, that's a Star Wars reference. None of you got it. That is just terrible. Excellent. Well done, you. You get 3 points. But we're not there to say this is the only path. We're there to say, well, different people within the Northern Territory in different sectors, be it the Chamber of Commerce and residents and ALEC and the government and different agencies and unions and so on, may all have different views as to what their preferred path is. We're not telling them which one we think is the best one. We're just saying if you're going to pursue one, this is the stuff you have to do, and this is the point at which, if you haven't solved it by then, that path is dead. There's decisions that have to be made over time, and if they don't get made, it's all over. So that's what the roadmap ultimately tries to do. Final thoughts for you to take out of this, and you're probably not going to want to think about energy transition anymore after this, but key things to understand that systems, we operate in a power system. It's not one component, it's how those components work together. So if you're it is a system, therefore we need system thinking. We have to think in the collective. Absolute numbers actually aren't that relevant. It doesn't really matter whether you get to 45% renewables or 51% or 62%. The actual numbers themselves aren't relevant. What's relevant is the rate of change and the relativity of those numbers. We're getting to points where those numbers are forcing change regardless of whether you want to argue about those decimal points. Uncertainty is actually a feature, it's not a bug. Everyone wants to know exactly how it's going to work. We're operating in an uncertain environment, but that's actually something we can use to our advantage because it gives us the opportunity to try different things. Collaboration is key, and consumers must be part of the discussion in a way that they haven't ever been before. If you think about how we use the internet now, the internet that I got access to in 1996, when I first got my modem at home and I logged into a bulletin board through the University of Melbourne, was all about a bunch of tech people who, here's a functionality you can use. My experience of that was irrelevant to everyone else, and it was irrelevant to the people who designed it. Now, our children who have access to devices that are beyond our comprehension engage with the internet because consumers have been put at the front end. Now, you could argue that that's possibly not a great idea, but the realities have been user experience and consumers have been brought forward in that area of industrial transformation in a way that had never been imagined, and we have to think about that in the context of the energy transition. So, that is Alice Springs Future Grid and 100 years of energy transformation for you in about 20 minutes. So, thank you.